Okay, for Chapter 8, we're doing addition reactions of alkenes. We need to predict the major products for the following reactions. We need to give structures of intermediates, include stereochemistry where appropriate. Okay, the first one is kind of tough to see the reagents. It's hydrochloric acid. So we will write these down at the bottom here. You have the alkene. HCl is going to protonate the alkene. We will generate a chloride nucleophile. The hydrogen will go on the least substituted carbon of the carbon-carbon double bond, and the carbocation then would be on this carbon, which is a tertiary carbocation. Then the chloride would come in, and the nucleophile attacks the electrophile to give the more substituted Markovnikov product. The next reaction uses bromine and carbon tetrachloride as the solvent. So this makes the three-membered Bromonium Ion. That's called a bromine. So Bromonium Ion is a three-membered ring. Basically, what you don't see here is the bromine bond. This double bond will make this three-membered ring with bromine. Bromine is large, so it's kind of just coordinating with both of those carbons. And then the bromide leaves. The bromide is now your nucleophile. And the attack here will be at the more substituted carbon, because that's the more delta positive. So those electrons then will come in and open this ring. And the stereochemistry here is anti in regards to the bromine. So you get an anti-addition of the two bromines to the carbon-carbon bond. This reaction here is called hydroboration of the alkene. And one of the carbon-carbon double bonds gets the hydrogen, and the other one gets the BH2. The hydrogen is going to go to the least substituted. This is going to be a syn addition, where the BH2 adds on the same side as the hydrogen. Then the second step is just hydrogen peroxide. So when you take this borane compound and react it with H2O2, it's going to replace the BH2 with the OH. So your product then will be an alcohol. And that will be an anti-Mark product, Anti-Markovnikov product. Okay, the next reaction we have here is an alkene with HBr, and we also have some per acid. So this is going to be free radical. The HBr and the per acids generate a bromine radical. So you can just take this bromine radical and do a half arrow addition to this alkene, and then one of those electrons will go to this carbon, and the other electron will form the carbon-bromine bond. And what you get is you get this free radical and this is a tertiary free radical. Then you have HBr, which is the next propagation step, and you get the hydrogen adding. And so that between the carbon-carbon double bond, the bromine adds to the least substituted carbon. So this is an anti-Markovnikov product. The next reaction here, we have HCl with peracids, but peracids do not generate chlorine radicals. So this is just going to be a Markovnikov addition. So we'll show the intermediate here. HCl, double-headed arrow. And the hydrogen adds to this carbon, so you get your carbocation on the adjacent carbon. This is a tertiary carbocation. And then you have your chloride nucleophile that will add to the carbocation to give the tertiary alkyl halide, which is a Markovnikov addition. This reaction, alkene with acid, a lot of times you'll see this with like sulfuric acid or H3O+. And the intermediate here would just be the hydrogen, the proton, added to the least substituted carbon in order to generate the carbocation on the more substituted carbon. And now you have the water nucleophile can add to that carbocation, and you will generate the Markovnikov alcohol. This is the Markovnikov product. The next reaction, it uses mercury acetate with the alkene. And so the first thing you do is you add mercury acetate. We've talked about this in class. And with water is your nucleophile. And then we'll treat it with sodium borohydride. So essentially what happens here is the mercury forms the Bromonium Ion, which it's very big. So mercury is going to kind of hang out on both of those carbons. And then water is your nucleophile, and it's going to add to the more substituted carbon. This is a Markovnikov addition. And you're going to generate this oxymercury compound. And this is why it's called oxymercuration. And then in the presence of sodium borohydride, the mercury acetate will get reduced off. Essentially, the mercury gets replaced with a hydrogen, and you get the Markovnikov alcohol product without any rearrangement. The next reaction here is chlorination, with water being your nucleophile. So with chlorine, you get a three-membered chloronium ion. The chlorine is kind of big and hangs out between the two carbons. And this carbon is your more substituted carbon, so it has more delta positive. Your water is your nucleophile. The water is going to come in, and you're going to get anti-addition. So this anti-addition here is shown with dashes and wedges. And the water, and it doesn't matter if you want to pick one going one way, OH, and then the chlorine going the other way. But that ring opening is an SN2, so it's backside attack. Proposed mechanisms consistent with the following reactions. So the first one here uses HBr and per acid, so that generates the bromine radical. Bromine adds to the carbon, and then these electrons split to give the more substituted free radical. And then the propagation step then would be with HBr, the free radical is generated, and this is your propagation step. You can see that that is the anti-Markovnikov product. Okay, so how do we get this reaction? Well, sulfuric acid protonates the alkene double bond. So we get the H acid going to the least substituted carbon, and then we generate a tertiary carbocation. We have a water nucleophile here. So those electrons then will add to the carbocation, and then you generate your alcohol. This is your tertiary alcohol, and it's a Markovnikov product. Here we have HBr, the nucleophilic alkene will get protonated, and those electrons then will kick out the bromine nucleophile. So you get this intermediate where the hydrogen goes here. You get your carbocation here. Now if the bromide goes in here, you get this product. However, if I was to ask this question, I would ask for the major product. And the major product is going to give the more stable carbocation. So this is a secondary carbocation. There's the carbon with the carbocation. And here's your neighbors, 1, 2. So that's a secondary. Well, if we switch places with this neighbor here, with the carbocation, you could get a tertiary. So you just look at the neighbors. Okay, so this has a hydride on it. So the hydride can shift. And you just show this by writing the hydride shift. And so that hydrogen then goes here, and the carbocation goes there, it trades places. Now if you have your bromide in there, you can add there and you get this product. Okay, here we have an alkene, an acid, HCl, so it's going to get protonated. They're both going to be secondary, whether you go on the carbocation here or the carbocation on that alkene carbon. So you get a secondary carbocation. Now your nucleophile is methanol. You do this by having a lot of methanol. So if the methoxy, the methanol attacks here, you get this product. If the chloride that's generated attacks, you would get this product. Show how you would synthesize each compound using, this is methylene, cyclohexane. It should be cyclohexene, ENE. Cyclohexene is your starting material, so you can make that correction. So basically, let's go to A. What do we need? We would need sulfuric acid, or some kind of H3O plus, and water. So what does that look like? Your alkene would get protonated. Get the hydrogen there. You get your tertiary carbocation, and then your water nucleophile, which is always around in an inorganic acid, would give you the tertiary alcohol. Okay, for the next reaction here, we get, let's look at it. So we have an alkene going to an alkyl halide. This alkyl halide, this is the anti-Markovnikov. It's an alkyl bromide. So that's just going to be HBr and per acids. Okay. The alkene going to the anti-mark alcohol. That is BH3THF. And then you react it with sodium hydroxide and hydrogen peroxide. And just to show you what that intermediate looks like, so you have BH2 going to one of the carbons and hydrogen going to the other carbon of the carbon-carbon double bond. The BH2 goes to the least hindered, the hydrogen goes there, and then upon addition of OH, this gets replaced, the borane gets replaced with OH. Okay, looking at your product for D, you have a Markovnikov addition, because it's at this carbon here, the more substituted carbon, and your nucleophile is going to be methanol. So the best reagents would be one, just use mercury acetate, and then react that in a solution of methanol, and then you could add sodium borohydride, and that's called alkoxymercuration demercuration. So your intermediate, remember, it goes this three-membered ring, merconium ion, and then this generates more of a delta positive here. The methanol then will come in and do a nucleophilic attack, open up that ring, and so you get OCH3, and then you get mercury acetate on the other carbon, and that gets reduced off with sodium borohydride. Sodium borohydride always delivers a hydride, so it's going to just replace that mercury with a hydrogen, and that's how you get your Markovnikov product. Okay, BD3. BD3 is, remember, D is deuterium deuterated, so it's just hydrogen isotope. So it behaves chemically just like BH3. So this is predict the product when 1-methyl cyclohexene. So draw cyclohexene, and then 1-methyl would be there, is reacted with BD3 and THF, and then you treat it with hydrogen peroxide, basic hydrogen peroxide, so throw in some sodium hydroxide. Remember that so here, deuterium is going to go to one of the carbons in the carbon-carbon double bond, and BH2, which would be BD2, will go to the other, and BD2 will go to the least substituted, and they'll go on the same side. So this is BD2, and this would be your hydrogen, and then your methyl groups there. The next thing you do is you replace the BD2 with OH from hydrogen peroxide. So what does that look like? That would look like that right there. Notice you have syn addition of the OH and the hydrogen. And that would be an anti-Markovnikov addition because the OH is going to the least substituted carbon of the carbon-carbon double bond. A routine addition of HBr across the double bond of a vinyl cyclopentane gave a small amount of the unexpected rearranged product. They want to know the mechanism. All right, so I'm not going to give you something this challenging on your exam, but what you do here is you get rearrangement whenever you generate a carbocation. So you're going to get a secondary carbocation here. And then you have to ask yourself, is that you know that's secondary because these are the two carbons next to your carbocation carbon. Now you look at those two and you say, okay, well, if I trade places with this carbocation with this one here, that would be a primary. Primary is not more stable than secondary. If I trade places with this one, it'd be a tertiary. So that would be. But notice that tertiary carbon doesn't have a hydrogen on it. Okay? So no hydrogen. so no hydride shift. But it can do a methyl shift. So what happens then is this bond here will break, and those two electrons will go to that carbon. And then this carbocation will go to this carbon here. And the best way to do that is to number them. 1, 2, 3, 4, 5, 6. That can be 7. So you see that you're making a 6-membered ring, which is, and number 6 is going to get the carbocation. So that's going to get your carbocation. So what does that look like? So this is 1. Here's 1, 2, 3, 4, 5, 6. So there's your 2. There's your 6. 6 has number 7 carbon on it. 1 has that primary carbon. So also 6 gets the carbocation now. As you can see, that is a tertiary carbocation. And you have the bromide nucleophile that can come in and attack there. As you see, that is the product that they showed here. Predict the major products of the following reactions and give structures for any intermediates. Okay, these reagents are, this is a peracid. Peracids look like this. So you can have acidic peracid. Like you all know hydrogen peroxide. Okay, so hydrogen peroxide has an oxygen-oxygen bond. These bonds are pretty weak. Okay, they're easy to break. And so if you react a peracid, this is called a peracid. So benzoic acid is a carboxylic acid. So this is the functional group you need to know is a carboxylic acid. So this is a peracid. You can see there's an extra oxygen there. So what happens here is when you get a carbon-carbon double bond, then these oxygens, it will deliver, peracid will deliver the oxygen to the carbon-carbon double bond and make an epoxide. Okay, so you go from an alkene to an epoxide. Epoxide is a 3-membered ring with oxygen. So here, this hydrogen is going to go here. Those electrons go there. These electrons go to that oxygen. Those electrons go there. So you end up getting the acid, and you end up getting an epoxide. So here's this carbon and this carbon. Here's this carbon, this carbon, and this is this oxygen. And that's an epoxide. Here you have the acetic acid. You can, the peracetic acid, you can just go ahead and take this off. We're not going to do that reaction. That actually opens the epoxide. All I would want you to do for organic 1 is to be able to recognize this peroxide, peracid, and make the epoxide. Here we have hydrogen and palladium. Notice it's also on the same side. It's in addition. So I showed that with the epoxide with the dash. Hydrogen on palladium catalyst. Remember, that's like here's your catalyst and the hydrogen gas. It's on there, and it's going to add syn addition. So hydrogen is going to add on the same side. You could have done this with dashes or wedges as long as the hydrogens get on the same side of the ring. Propose a mechanism consistent with the following reaction. Okay, so you've learned how to make epoxides using per acids with alkenes. This is a three-membered ring, but they're only carbons, just only carbons. And so this is a cyclopropane ring. And you can do that with alkenes with these reagents. So you've used chloroform. Chloroform is CHCl3. You use that in NMR solvents. Well, this is bromoform. And basically, that hydrogen is pretty acidic. You could probably look up the pKa and see. So when you put the bromoform in sodium hydroxide, it basically generates, it takes away the proton and the bromine leaves to give you this carbene. So all you got to do is generate the carbene. It's a carbon with 2 electrons and 2 bromides. And then what happens is it'll add to this carbon, and then these electrons will add to this carbon to form the cyclopropane ring that you see here. So I can draw this out for you if you want. All you have to be able to do is when you see these two reagents to generate your carbene, so write carbene, and then you could draw your electrons. This goes here and that goes there to give you your product. Show how you would synthesize each compound using methylene, this is hexane again, ENE as your starting material. Okay, so the first one we make is a diol. So the diol reagents are, you can use potassium permanganate. It needs to be cold and dilute. So you could use osmium tetroxide, and then you need to use, you just write osmium tetroxide. For B, so all you gotta do is the reagents here. B, so that's a diol for A. This is a cyclopropane, and you want to use basically CH2 carbene. So you need to use a carbene, a CH2. There's 2 ways to do that. You could do CH2N2. This is called diazomethane. And you have to react this with light. Nitrogen is your leading group to generate your carbene. They don't like that reaction because it's dangerous, it's explosive and toxic. The other way is the Simmons-Smith reagent. So you basically react diiodomethane. It's kind of like you all have used dichloromethane in the lab. Well, this is diiodomethane. And then you react it with zinc copper couple, and that iodide and the CH2 and the zinc insert between each other and generate the carbene. And that's how you make a cyclopropane. C, you're making a chlorohydrin, so you need to add chlorine, and chlorine will make your chloronium. So I will draw that over here. So you get a chlorine 3-membered ring, the chloronium ion, and then you react it with water, because you want water to be your nucleophile, and then water will come in and open that 3-membered ring, and that's how you get your chlorohydrin. This is an epoxide. Epoxides, basically you just react it with something like this. This is a per acid, or you can use MCPBA. That's my favorite reagent, and that is metachlorosilane. Benzoic acid. You do not have to know the structure, but you do need to recognize MCPBA, and that makes an epoxide. And then E, you're doing a cleavage of this alkene, and so ozone and DMS will reduce that to your ketone. And that would be the best way to do that. Okay, limoene. Here's limonene. Gives lemons their tangy flavor. So we're going to react an excess of these reagents because we got two alkenes on this molecule. So we're going to react both alkenes in these different reagents. Okay, so the first one is BH3THF. And then we're going to treat it with basic, so that's sodium hydroxide and hydrogen peroxide. We make Anti-Markovnikov Alcohols. So the first one is going to be here. We can either put the alcohol on that carbon or this carbon. We're going to put it here because it's the anti-Markovnikov. And then we come down here and we either put it on this carbon or this carbon. And we're going to put the OH here because it's the least substituted of those two carbons. And that's your first product. Okay, the next one is metachloroperbenzoic acid. This is MCPBA. And for this one, we will make an epoxide. And we just show the dashes because we want to show the stereochemistry. And so there's your epoxide. Okay, now we want to do ozone and dimethyl sulfide. So that's going to cleave each one of those bonds. So the best way to do this is to redraw. And then you're going to cleave this bond, and you can cleave this bond. So this one is going to make a formaldehyde. That's that carbon. This carbon is going to make a ketone, and we're at this carbon, and so let's branch out here. 1, 2, we'll go to this one, 3, come here, 4, and then that's going to make a ketone there. There's that CH3, and then let's go here. We're going to go back to there, which is here. Go on this side here, and then we go here, and that's going to make an aldehyde. That one's kind of tricky, but that's what ozone does. It will cleave the carbon-carbon double bonds, and if it's disubstituted, like this one, you get a ketone. It's a ketone. If it is monosubstituted, then it has a hydrogen here, so it becomes an aldehyde. Okay, so that's an aldehyde. Okay, hot concentrated potassium permanganate. So KMnO4, hot concentrated. You're going to cleave again, but this time you're going to get either a ketone or a carboxylic acid. So let's just look at what we generated for the first one. And wherever you get a ketone, you're going to still get the ketone. But where you got the aldehyde, this time you're going to get a carboxylic acid. And then that would actually go to carbon dioxide because that's the highest oxidation state. I really would care that you understand ozone and the MCPBA and the hydroboration. I like potassium permanganate mild, where you make the diol. I'm not so interested in the cleavage. Okay, let's keep going. The next one is peroxy acid and acidic water. You don't have to do that because that's ring opening, and we're not going to do that. You do need to know this one, hydrogen and platinum catalyst. So that's H2 on platinum. You can have it on platinum, or you could have it on palladium. So this basically will add hydrogen on the same side. Wherever you see your double bond, you get hydrogen on the same side. That makes an alkane. So you're going from an alkene to an alkane. Hydrogen bromide gas. So HBr. We're going to add the H, generate the bromide nucleophile. This is going to add Markovnikov addition to each of these alkenes. So you're going to get your carbocation here. And so you're going to add the bromide to the more substituted carbon. So that's Markovnikov addition. If you put it in a solution containing dimethyl peroxide, what does that look like? That's your ROOR, HBr. Now you're going to get the anti-mark. So when you have those two to choose from, it's going to go on the least substituted. So this is your anti-mark product. Bromine water. Bromine and water, that means water is your nucleophile. So the best way to do these is to draw your three-membered ring, your bromonium, and then your water nucleophile is going to add to the more hindered, the more substituted. So when the ring opens, you need to show anti-addition. So that means the OH is coming at you and the bromine is going away. Same thing here. This OH will add to this carbon, and you can show just anti-addition here. That's bromine water. Chlorine gas. We got three more here. Chlorine gas. So all you have is chlorine. It's going to make the three-membered ring. Intermediate, the chloronium. And then your chlorine gas is going to come more substituted, and it's going to add anti. So you can just go ahead and draw your chlorines in an anti-fashion. And that would be the correct answer for that. Okay, mercury acetate and methanol followed by hydrogen peroxide. Do that over here. So you have 1 mercury acetate, methanol. Okay, that's your nucleophile, methanol. We'll go ahead and write that in red, methanol. And then the second reagent is sodium hydroxide. That actually should be sodium borohydride. Sodium borohydride. Okay, so draw your Bromonium Ion. So it's very good if you draw your intermediate first, and then you can have your nucleophile opening from the more hindered carbon. And then you can just go ahead and replace the mercury with sodium borohydride. So that would be OCH3, and then you would get the hydrogen at this carbon, so we won't even draw it in here. And here you get OCH3. So this makes an ether, and it's at the more substituted carbon between the carbon-carbon double bond, so that's Markovnikov addition. All right, this reagent here is going to generate a carbene. So CHBr3 and sodium hydroxide generates a CBr2 carbene, and with your alkene, so if I draw this alkene again, you're going to make a cyclobromide. So bromide top and bromide bottom. Cyclopropane, alkyl halide. Okay, this problem, go ahead and make the correction. The bromine should be anti. And so what is a suitable alkene? So you're going to add bromine. And so the suitable alkene would look something like this. And then that reagent would add anti-bromine addition. Okay, this alkene here, that would be a suitable alkene, cyclohexene, and the reagent would be chlorine and water. So you'll make your three-membered chlorine, onium, three-membered positive charged ring, and then the water will add and open that ring. Okay, this alcohol would be a anti-Markovnikov alcohol. So between these two carbons, it goes to the least substituted one. And to do that, you have to add borane, and then you treat it with hydrogen peroxide and sodium hydroxide solution. This reaction, the product is an ether. So this is from this nucleophile, and this is a Markovnikov addition. And so the suitable alkene would look something like this. And to do that reaction, you would need mercury acetate and methanol for your first reagent, and then you will reduce it with sodium borohydride. Okay, alpha pinene. These are called road maps. They're kind of fun. You basically are going to go through all the different reagents here. And the key here is to look at this compound here and recognize that this is ozonolysis. So ozonolysis, which means ozone will break these bonds. And so you draw everything, and this is an aldehyde, and this is a ketone. So we need to draw those back together for this alpha pinene structure. So to do that, you draw this, and then we will go from here to here to here. So from here to here to here, we have a double bond, and that's an aldehyde. So there's your hydrogen. And then from this carbon, we go from here to here to CH3. So that is your alpha pinene compound. All right, and then if we treat this with bromine and water, our product will be, let's try to draw this, let's see. Try to draw a diamond here. with 2-methyl, 1, 2, double bond, CH3, and then that carbon-carbon double bond, you get the bromine, positive, and then your water will come in and attack here. So B product would be, hardest part is just drawing this. OH and Br there. There you go. And you can count that. C10, so you get 1, 2, 3, 5, 6, 7, 8, 9, 10. And you should have 17 hydrogens, 1 oxygen, and 1 bromine. So that's the structure for B. Now, if you take this compound and you heat it with sulfuric acid and heat, okay, you're going to lose water. And so where do you lose the water? You got to lose the water on the neighboring OHs because it's going to get protonated to make a good leaving group. So that gets protonated. Now it's a good leaving group. And then the hydrogen either comes from this carbon. It can't come from this carbon. 1, 2, 3, because this would be a bridgehead carbon. That's a bridgehead carbon, and that would violate Brett's rule. And so it's going to likely be this structure here. There. Because that is bridgehead. So that is the product for C, and you could count those. All right, for A, you're taking this alpha pinene structure, which is right here, and you're reacting it with bromine. So A should look like anti-bromine there across the carbon-carbon double bond. That's structure A, and you can do the molecular formula. Okay, for structure D, we have a peracid. Peracids make epoxides with the alkene. And the CH3 would be on the other side. So that would be your structure for D. And then E, you don't have to do E. E is acid opening of epoxides, and you'll do that in organic too. Okay, predict the major products of the following reactions and give the structures of intermediates, include stereochemistry. Okay, so this is ozonolysis. So this carbon here has a hydrogen, and so it would, when this cleaves, it makes an aldehyde. And then this carbon here has a methyl here and an ethyl here. So it is going to make a ketone. So there's the products. Osmium tetroxide and hydrogen peroxide is going to give you a diol. So, and it's going to be on the same side. So you can just draw your diol on the same side. You can use dashes or wedges. Permanganate co-dilute is going to give you a diol. It's going to be on the same side. So the OHs both get dashes. Warm and concentrated means you're going to cleave this. And so this will be a ketone. Now when these cleave though, so 1, 2, 3, 4, 5. They don't give aldehydes like ozonolysis. That will go to a carboxylic acid. So you can count 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This is ozonolysis again. So we're going to cleave this. This carbon will be a ketone, and this will be an aldehyde. So you can draw your aldehyde, and you have 1, 2, 3, 4, 1, 2, 3, 4, and then this would be a ketone. You can count them all, 1, 2, 3, 4, 5, 6, 7. Okay, this is called ring metathesis reaction, and it combines the rings. And the metal can be either Grubbs catalyst, or it can be Schrock's catalyst. The metal is usually molybdenum or ruthenium. So when you see this reaction, basically this is called a ring closure metathesis, RCM. I'm not going to do any other type of ring metathesis reactions for you, but this cleaves and this cleaves. These will combine to give you CH2, CH2, and then these rings will combine 1, 2, 3, 4, 5, 6. So this is going to be 1, 2, 3, 4, 5, 6 cyclohexene and the alkene ethene. You always get the ethene for these because they switch places. Now, and you can always count 6 plus 2 is 8, and so you have 8 carbons. Okay, so here we have polymers. Alkenes can react together to make a lot of the polymers you see. You've heard of PVC pipes, and that's the V stands for vinyl. The C stands for chloride. The P is polyvinyl chloride. Okay, so basically you would put a little catalytic acid in these, so you would get H3O plus, and so this would generate the carbocation, and then it would react with itself. So when you have an alkene, the alkene will react and with the carbocation. So this says, let's draw the chlorine here. So this is the chlorine here on this carbon. And now we have this carbon here, the new bond, and we have the chlorine here, and we have the carbocation here. Now, this carbon has 2 hydrogens, and so when this gets deprotonated, you get and this is poly, and this is a vinyl group right here, vinyl chloride. So that's how you would react to make polyvinyl chloride PVC pipe. Okay, carbon tetrafluoride. So you would buy some tetrafluoroethylene, you react it with acid to get this just a little drop of acid, and this would generate a carbocation. You would get the protonation there, you would get your carbocation, and then it would react with itself. So this would go here. You would keep generating the carbocation, and it would just keep on going and keep on going. And that's how you get Teflon, tetrafluorocarbon, and it's a non-stick coating. Okay, the next one is acrylonitrile, and once again, you add a little bit of acid. This is what's used to make sweaters and carpets. This gets protonated, and you generate a carbocation. The carbocation would probably be more, it would be there because that would be the more stable, and then it would react with itself. So this would nucleophilically add to this carbon. So you would redraw that, the new bond, and that bond would be right here. And then you get a carbocation, and then it would just continue to go, and that would be polyacrylamide or acrylonitrile. Okay, the catalytic polymerization of isobutylene. So here it's 2-methyl propylene. So propene right here, 2-methyl propene. This is also called isobutylene. See how it makes the Y groove, and there's 4 carbons. It is often polymerized under free radical conditions. So you can just write a free radical such as that, and then you just show free radical. So you want your more stable tertiary radical, and this would generate the OR, and then it would react with itself. That's what you always want to do. You want it reacting with itself. So it would form here, that would form here, and once again, you just redraw this and show the new free radical, and then it just continued to react with itself. Show what products you expect from the following metathesis reactions. So these are ring closure metathesis. You can see the metal with the double bond, and so these CH2s are going to come together and make ethene, and then you can count the ring closure: 1, 2, 3, 4, 5, 6-membered ring. So then when you draw the product here, here's your oxygen and your 6-membered ring, and actually, where's the double bond? The double bond would be between this carbon and that carbon. So it would be between these 2 carbons here. Okay, this one here, this CH2 and this CH2OH. So that would look like this. CH2OH, and then this will be 1, 2. Well, I'm sorry. No, this is not a ring closure reaction. So I'll draw the product here, but like I said, I'm not going to ask you on a quiz or an exam unless it's a ring closure reaction. I just think they're a little simpler. But 1, 2, 1, 2. So there's that carbon. And you're going to get this one here, double bond CH2OH. So I could ask you the top one and the bottom one. Here we're going to have the CH2, and then we're going to have 1, 2, 3, 4, 5, 6, 7, 8. We're going to have an 8-membered ring. I'm going to draw a stop sign here. And this is this carbon and this carbon. And then I'm going to fill in my heteroatoms oxygen. And that is that. Okay, give the product expected when the following compounds are ozonide and reduced with dimethyl sulfide. All right, so we're going to cleave these reactions. So this would be here, and this has a hydrogen, so that would give you formaldehyde for this carbon. And I think we have a 7-membered ring. This would give you a ketone. And then this right here would be an aldehyde. And this one also would be an aldehyde. So let's count the carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yep, so there's your dialdehyde. Okay, here we have on this one, we're going to cleave it right here. So this carbon here will be an aldehyde, and this carbon here would be a ketone. 1, 2, 3, 4, 5, 6. And so there's your ketone and there's your aldehyde. This is actually called 1, 2, 3, 4, 5, 6, 2-hexanone, O-N-E for the ketone. And this would be, there's 2, this would be ethane, but you drop the E and add Al for aldehyde. Aldehyde. Okay, so we're going to cleave this bond here. This carbon will be an aldehyde, and this carbon will be an aldehyde. So we redraw the structure, a bicyclo structure, and this carbon is an aldehyde, and this carbon is an aldehyde. Okay, here this is alpha pinene, so I think we've already worked this problem. We cleave it right there. So this would be a ketone, and then we just redraw. And then this carbon here would be an aldehyde. So then we can count the carbons. 1, 2, 3. 1, 2, 3. And then 1, 2, 3. There you go. Okay, so we're trying to get the unknown alkene, and it reacts with 3 equivalents of hydrogen on platinum. So that means we have 3 alkenes. We're reducing 3 alkenes. And the final structure is 4-methylcyclohexane, 1-isopropyl. And so we have 3 alkenes. This aldehyde would have to come from this because of the 2 hydrogens. So we can start there because ozonolysis. So you can go ahead and there is that alkene. And then that means this is, so we'll call this number 1. That's number 1. And 1 has to be bonded to what? So if 1 is bonded, if this is your CH3, if that's your CH3, and this is bonded to 2, that would be your 2, and then you would have another carbon-carbon double bond here, because this would be here, and that would be, so that would be 2, and then this would be your CH2 here, and then this would be your aldehyde here. So there's your hydrogen. And then you make sure this would bond with this carbon here. It should be this carbon. That's your CH3. And then this is this carbon here, methylene. And then this is an aldehyde here that would be bonded to the 2. So that would be your starting material. Okay, so an unknown compound decolorizes bromine in carbon tetrachloride. So it's just saying you have an alkene. It undergoes catalytic reduction to give decalin. So you have an alkene, and when it's treated with potassium permanganate and hot, concentrated, warm, concentrated, then it's going to give you this dicyclic, or this acid. So you have an alkene, and your alkene would look something like this, because you can imagine that this would get reduced with hydrogen and platinum to give you decalin. And then if you reacted with potassium permanganate, you would cleave these 2 bonds here, and this would be, I guess, need this stereochemistry here. So this would be OH, COH, COH, and then this right here would be the oxalic acid.